Yeah, so welcome to my talk, Build Living Stuff. So I'm Kristoffer Deinoff, and this is how I look normally, and this is how I look on the inside. This is my DNA, something I extracted last summer, I guess, when I first learned this stuff. And DNA, if you might not know it, it consists of four chemicals, A, T, C, and Gs, and they are building blocks of all living things that we know. It's also what I like to call life code. It's not that different from the zeros and ones that we are used to. When an apple drops to the ground and starts making roots, that's genetic sequences that are executing. So this is life code. So we have been doing this. We have been playing with this for a few years. So the phase one of life code is reading it. So this is Craig Venter. He started a project called the Human Genome Project in 1990. They went on for 13 years, and they took 13 years to sequence the first genome. It cost $3 million. And it took a long time. Second time, a couple of $100 million. So the price decreased quite a lot. He's been asking the question for some time now. What is the, you know about the MVP, minimum viable product? He is talking about asking, what's the minimum viable number of genes for a living organism? Then you have this guy, Juan Enriquez. He is the founding director of the Life Sciences Project at Harvard, and he is, if you look at some of his talks or read some of his books, you would understand why his Wikipedia page says that he's one of the world's leading authorities on the economics and political impacts of life sciences. And he started in 2003 a company with this other guy called Synthetic Genomics. We will come back to that later. And he has also written a book called Homo Evolutus, Meet the Next Human Species. He's arguing that we can no longer, or soon can no longer, call ourselves Homo sapiens. We'll come back to that as well. And in 2003, he predicted that in 5 to 8 years, we will be able to sequence a full genome for $1,000. So that's a pretty big step from the $3 billion it cost the first time. So let's take a look at how that went. So this is an exponential graph. So the white line you see there, that's Moore's law, which we're all familiar with. So up until 2007, we were pretty much following Moore's law. And that's okay, but that's not enough. And there's a quote that Juan Enriquez likes to use from Lenin. I think it's a little bit rewritten, though. But it's, there are decades where nothing happened, and there are weeks when decades happen. So we hit a point in 2007. And if you can look at the baseline, the lowest line here is $1,000. So we have practically hit his target. A few years later than expected, but still. So it takes approximately $1,000 to sequence the genome, and it takes 1 day, single day now, from 13 years. So we've come a long step. So, phase 2 of life code, copying it. You all remember Dolly, right? The sheep, the cloned sheep, first animal that was cloned from paternal cells. This is the actual Dolly. You can find her at the Museum of Scotland, where she's taxidermied. And you remember we had a lot of, I don't know if any of you have seen this South Park episode. It's about using stem cells and stem cell research. And if you remember, there was a lot of discussion about this in the early 2000s. A lot of people against it because you had to use stem cells from embryos that were a few days old. But then you suddenly stop hearing about them. Have you ever, any of you heard that discussion in the last 10 years? No. Why is that? Well, these four guys are responsible for that. In order to explain what those four chemicals does, I have to explain a little bit about how stem cells work. So if you can picture yourself a mountain, and you have the stem cells at the top. So first they multiply, and if when they have divided 16 times, there's not enough room for everybody on the top. So some of the cells go down one side of the mountain, it becomes bone cells. Some cells go down the other side of the mountain, becomes lung cells and skin tissue, and you get the point. But once you go down the mountain, it's really, really hard to go back up. Unless, of course, you have a ski lift. And this is what Yamanaka in Japan found out, that if you put these four chemicals on any living cell, they will revert back to a stem cell. That's why you haven't heard this discussion lately. So we've basically engineered around that problem. So, and this also works for human cells. So we can take skin cells, put these four chemicals on it, and go back to a stem cell. Then we can make that force to differentiate into the cells that we want. So we have made functional liver cells from a patient's skin cells. And it opened up for things like this. You can take a skin cell from one mouse, revert it back to a stem cell, then you grow these in a lab. And you can grow several new mice, clones. So that basically means for any living organism, you can take any of its cells, put these four chemicals on it, and then you can make a full copy of that living organism. So does that mean you can make your own clone army? Well, in the future, probably, yeah. There are probably some ethical discussions we should have before we get to that point, but and we also get things like this. Juan Enriquez, he was running around a farm in Argentina, and he was looking at this cow, and then he came across these two cows, and they looked quite similar. So he was running around and taking a lot of pictures of them. And a guy came up to him and said, "But why are you taking all these pictures? Don't you understand? They're all the same." These cows are not that special though. This one, next one is. Phase 3 of life code is editing. So this cow was born a couple of weeks later after Juan was there. This is quite special because this cow, it produces a substance used to treat cancer in its milk. And of course, this is not the only one. You have these ones who produce insulin in its milk. You have this goat, we call it the $1 million goat because it actually cost $1 million. It produces insulin in its milk. This was approved in Europe in 2007, by the FDA in the US in 2009. So we already had this for approximately 10 years. And of course, you have these guys down in Argentina as well. They really like cows, which have put some of the proteins that you can find in human mother's milk into the genome of the cow, which makes the cow produce more human-like milk and with more correct nutrients for humans. So basically, the last 4 billion years, first 4 billion years of life on this planet, life was governed by these two principles: natural selection and random mutation. This is what Darwin wrote about. But we are moving to another era. First, a natural selection. We have been doing this for a long time. 2,500 years since we first realized that we could change the mustard seed plant to, I don't remember which of the variants, but if you force the mustard seed plant to grow in different directions, you can have it grow broccoli, kale, kohlrabi, and a lot of other fruits. So if you go to your supermarket or your grocery store, almost none of those things you can see there are natural. They're things we have made. But of course, we have been relying on the random mutations and reproduction for doing this. It takes a long time. It has been an unsure process. What we're beginning to do now is using non-random mutations. And we don't have to wait a generation to see the results. So this massively speeds up the process. And then you get competitions like this. The IGEM, the International Genetic Engineered Machine Contest. It has been running for a few years now. And what they do, what they were originally trying to do when they started this was asking the question, can simple biological systems be built from standard interchangeable parts and operated in living cells? And yeah, they can. And you have some really cool projects that these students have made. First, this is the library, standard library of genetic parts, which you can go online, download, use some software, and you can synthesize or connect your own cell. Some of the projects that they have made with this are organofoam, or organic styrofoam. That's nothing new, but organic styrofoam has a problem with mold. So they made a version, a genetic modified version of organic form that degrades in about 1 month in the ground, opposing 500 years for normal styrofoam. You have this. It's a small kit, the Darwin Toolbox. For $1,000 you can buy this, and it contains everything you need to edit genomes. You have this little machine. This is a machine that will detect antibiotics in milk products, in dairy products. And of course, you have the B. coli. You heard about the bees dying all around the world, didn't you? Well, turns out it wasn't Monsanto. It was a very nasty. It was a very nasty. Not bacteria, but parasite. Nosema ceranena. The Taipei team, they made something which, to try to tackle this epidemic, first it will try to stop the infection. But if the infection stops, it will try to treat the infection. And if it, within 120 hours, is not able to treat the infection, when you get the risk of spreading it, it will kill the bee, so it won't spread. And of course, you have a cellular version of Minesweeper, which you play in a petri dish with small pipettes. And you have a Taxi coli, which is a drug delivery mechanism. This is just a sketch for doing this, but it's a very promising thing. So it basically takes a nanomedicine, transports it to a specific part in the body, and then releases the medicine at that specific point. So, phase 4 of Life Code is creating. So Craig Venter and Juan Enriquez, they started this company, Synthetic Biology. And in 2010, I believe, they created the first synthetic cell. They created this, created a DNA. They took Mycoplasma bacteria and inserted the DNA into that cell and made that cell reproduce with the new DNA as the new organism. That was the first time. And you remember the question that Craig Venter had, that what is the minimum viable number of genomes in the cell? Well, we got one step closer to that question this year, actually, when they made the next version. This has 473 genes only in its gene code, and 149 of them we don't know what does yet. So this is as far as small as we can get. And of course, 1 month ago, 2nd of June this year, we started the Human Genome Project, RIGHT, which aims to synthesize a full human genome from scratch. And another thing that has happened also, we made a new base pair. You remember the A, T, C's, and G's? Well, we have made X and Y. And we have made organisms that reproduce this and export this into RNA, into cells. We don't know what to do with it yet, but potentially we can create totally new life forms that have never existed before. And then you have DNA origami. In 2008, there was a TED talk by Paul Rothermund. He was using small bits of RNA to tie it together and form longer strands of RNA. RNA is single-stranded DNA. DNA is double-stranded. So basically, they made a system for creating objects with RNA. And they made a lot of them, a lot of different. So we have a world map, you have some text, and you can see that not all of them are perfect. And what this starts to get interesting is when they asked, is when he said that my friends, molecular programmers and I are interested in using DNA, RNA, and protein and building new languages for building things from the bottom up using biomolecules, potentially having nothing to do with biology. And what they also found that they could put these, they can make a grid with these RNA strands, and they, some of his friends, they were able to make a switch and a small transistor, if you might say, and they made that work. And they used this grid to place those different circuits to operate with each other. This got me really, really excited, and in 2010 I sent a tweet out into to the world, never expecting a response. I did get a response from a professor in Ann Arbor in the US though, but we weren't quite there yet. And if you don't know what ECJ is, it's a Java-based evolutionary computing platform. That's how I got interested in the AI actually. But then this year, at MIT in March, I believe, we got Cello, the world's first programming language that compiles into DNA. So what you do, you go to cellocat.org, you create a user, and you log in, and you get this interface. Does anybody know, have anybody heard of Verilog? Verilog is a programming language for a hardware programming language used to create computer chips. This language is based on Verilog. So here you write your Verilog code. So here I've selected 2 inputs and 1 output. And I only give an output signal if both input signals are present. So you give it a name and you click run and you get all these fine charts. If you know about low-level computer stuff, you might understand this. I don't. The more interesting thing is this. This is the genetic output, which you can send to a lab. They will synthesize it for you and send it back. There you can insert it into a cell if you want. Now things are starting to get very interesting. But how do you get this into stuff? Well, meet CRISPR-Cas9. It's something we found in yogurt. It's a defense mechanism against viruses. But we found out how we can use this in another way. Because what it does, you have this matching sequence, which goes out, finds a specific part of your DNA, of your genome. And it makes a cut. And basically, you can remove parts, you can fix parts, and you can add parts. So what this does is it basically, and it literally transfers the process of editing genes to how we edited silent movies back in the days. It's almost the same as if you cut and paste. And you can do this in your home. These 2 guys have built their own CRISPR labs in their home for approximately $1,000. Then you also can do that. So what do you call people who are doing science and doing this at home? You call them scientists? They've never gone to any school and learned this stuff. In IT, what do we call self-taught programmers? Well, we call them programmers. Yeah. So I would call these scientists, even though they have no scientific education. And some of the cool things that prop up after this is you get companies like this, glowingplant.org. You can go online and you can order your glowing plant or a starter kit, in which you can turn your plants at home to glowing plants. They have some legal issues delivering it, but they're in the demo stage with the maker kit. They have delivered it to a couple of schools in the US. I think their first product is going to be a fragrant moss with different smells. I think that's going to be their first product to market, though. So, up until, if we go back a second, up until we experienced CRISPR-Cas9, all of the things we have been talking about has been done by synthetic biologists. When we get here, we don't need that anymore. And especially if you think about the cello programming language, you really don't need to know anything about biology. You only need to know about digital circuit or logic circuits. Of course, if there are a lot of circuits in the computer chip. So I really hope that somebody sits down and writes the first biological chip with this program. Of course, the cello is at the current stage, it's tailored towards E. coli. But this is the first stage. So, where do we go forward with this? You know about DuPont? Huge petrochemical company. 2014, fourth largest petrochemical company in the world. They basically make everything out of oil. Well, in 2012, 40% of their earnings were life sciences based. Did you know that these companies were doing this? There's a lot of companies investing a lot of money into this. They're growing bacteria who does stuff. They have made bacteria that they're growing a form of polyester that feels like silk, and they do it inside corn. So last year they merged with Dow, and now they want to spin off their petrochemical business at large and want to focus all on life sciences. And as the CEO stated that the first 100 years we made explosives. Oh, typo. The next 100 was modern chemistry, and about 20 years ago we started biotechnology. The next 100 years will be going to be about interacting the sciences. So what can we expect in the future with this? Well, you can expect we will have personalized medicine that are tailored to your specific DNA or genotypes. That will help with a lot of the reactions we have to medicine today. We'll be able to have targeted delivery systems of drugs, so we don't have to flush the entire body full of drugs when you want to treat a specific part. We will have 3D printed human organs. We already do this. We make these stem cells, as we say. We make a scaffold, we spray them on, and then it grows. We have made functional heart valves doing this. Superhumans. So, approximately 100 years ago, hearing aids. They were like these big tubes, right? Now today you have cochlear implants, which you implant into your ear so deaf people can also hear. So this technology is improving, right? And we're going to get to a point where it gets as good as our own air. Do you think the scientists will stop them? No. And we're also doing this with sight. We have made stuff that makes blind people able to see a difference between light and dark. And we're also going to get to the same point there. So, physical properties. Do you have an ACE gene? Why is that important? Well, nobody without an ACE gene has climbed a mountain peak over 8,000 feet without having an ACE gene. Or more specific, 577R genotype. If you don't have that, you might not want to get into sports because almost every male power athlete ever tested carries at least one of these types. So we're going to change a lot. And yeah, resurrection of extinct life forms. We have already resurrected an old plant. Some people would say that, well, this is playing God. We shouldn't interfere with nature in this way. But if you really think about it, our interference made a lot of those species go extinct in the first place. So do we have an obligation to do that? Or this is a discussion that we really should have. So I have a couple of ideas, my own, I have been thinking about a little. So once, a few years ago, I heard a doctor explaining how doctors diagnose disease. So let's see you have a symptom, something in your arm. Say this, the system, the function that's not working, say it has 4 parts. Doctor doesn't know which part, so he gives you medicine he knows works on one of the parts. And then you go home, and then you wait, and then you come back, you see if it works. If it works, cool. If it didn't, then he gives you another medicine. It works at the next part. This makes diagnosis takes a lot of time. So one of my thoughts was, wait, what about if, you know, this drug delivery mechanism? What if we can make a small biological machine to go to each of those 4 places and listen for the signals that should be coming? And then you just take a blood sample or a urine sample after that to make the diagnosis. It will shorten the process. Okay, this is not possible today, but it will probably be possible to do. It's one of the things that I would like to do. Another things I would like to do is make small versions of big animals. I would like to have a small hippopotamus at home. And I'm probably not the only one. I also do want to have, and this is actually serious, if I can find, I don't want to be a single parent though, but if I can find a woman crazy enough to live with me, I want to have 2 or 3 kids. 1 natural, 1 clone, and of course, if I want a clone, then she'll get one as well if she wants. So, I've been going a little faster than expected, but I will, before we start ending, I will do a little poem I'm in the process of writing. So, what if humankind were to evolve? Which direction do you think that humanity would grow? And what if we ourselves were in control? Which genes would you select, and which ones would you let go? And which ones would you create if this suddenly becomes just as easy as baking a cake? Do you realize what's at stake? So, if you could choose an upgrade for your body, would you choose a greater mind or being a hottie? Some have already augmented for magnetic sensing fingertips to feel the electricity around them. Or maybe you would like to hear the colors you're used to see, or maybe see the infrared or ultraviolet. Or have a plug-in for your brain with an external HD, so when you have a good experience, you file it. These are some questions that we really ought to know the answers to before we upgrade to the human 2.0. Because we're on the verge of a species evolving, branching different directions for all the problems we're solving. And it's not a question of if, but rather how we'll get through this and emerge on the other end as Homo evolutus. So, to end up my talk, I will use the ending statement from Juan Enrique's last TED Talk in last November, December. This is the single most exciting adventure human beings have ever been on. This is the single greatest superpowers humans have ever had. And it would be a crime for you to not participate in this stuff because you're scared of it, because you're hiding from it. You can participate in the ethics, you can participate in the politics, you can participate in the business. You can participate in just thinking about where medicine is going, where the industry is going, and where we are going to take the world. It would be a crime for all of us not to be aware. And I was not able to get the ingredients in time, but I do have some fun stuff over here. So if you come over there at 5 o'clock today in the lunch break, I can teach you how to extract your own DNA. So at 5 o'clock that will be. And I seem to have used a lot less time than I predicted. Well, I usually do that. But with that, and if you want to take a look at this, this is some DNA I extracted a couple of days ago. You can just come up and have a look. And with that, I open up for some questions. Yeah?
Some security concerns about it. We recently knew about this one of the first fatal Tesla incident where the driver was not actually taking care of how the car was driving. But of course, a consequence for this can be much more fatal than that. So is there some work going to address this security, this potential damage concerns?
Yeah. This is a discussion we should be having. We should have started this discussion several years ago, but we're not having this discussion. We really should start talking about this. We should decide how we want to approach this, because it's going to happen, either you like it or not, because this technology is going to be so available that anybody can do it, at least a lot of the parts. So we need to find ways, we need to decide what to do and what not to do. We really don't want to end up in a situation like with the atom bomb, that we first deploy a few atom bombs and realize, oh, maybe we shouldn't have done that. Maybe nobody should ever do that again. We don't want to end up there with this. More questions? I can't hear. Can you get the microphone?
Just to continue on the previous question, do you know about any countries having some already legal stuff, like laws installed for this kind of activities?
Well, you have some biotechnology laws in place. That's why the glowingplant.org, they have legal issues of getting this fully to market. And many countries have laws that are very restrictive in these areas. But that's probably going to change, because we are going to be able to do so much great stuff with these things. We're going to be able to treat diseases we've never been able to treat before. We're probably going to live longer than any other generation that haven't done. Or within this century, we're going to reach heights that we've never been able to fantasize about. If you think that the development we have had within computer science since the 50s have been great, or within your lifetime, then you can just buckle up and lean back, because this is going to be a one hell of a ride.
But the concern is, even if some countries, progressive ones, will install some prohibitive laws and stuff like that, but there will be still rest of the world, and you can create a lab and do some really crazy bad stuff with it in Asia or whatever. But
sure.
So consequences could be anything really.
With this, you can produce probably produce genetic specified diseases which only target specific groups of people. And that's really scary thought. We should decide. All of us should decide of not doing that. before somebody does. That's why we really need to start talking about this. Because it's not some distant way in the future. This is happening now.
Hi, thanks for the nice talk. It's really inspirational. Do you know the CRISPR gen editor kit, something like that?
Yeah.
Can you give some insights? How does it work? And is it actually something to have a look at? Because the guys are actually trying to sell the kit for 500 euro, I believe, which you can use to edit genes in the living creatures already. Is that true? Does it work like that?
Well, from the article where I took these pictures from, they just ordered their specified CRISPR genes in a small package, which they use at home to do this stuff. Most people make glowing plants, and the fluorescent protein is one of the easiest to extract and implement. That's one of the most common ones nowadays. But we're going to do much more advanced stuff very soon.
Thanks.
And one of the other fun things is that we're now at the point where, within biotechnologies, and at least with the release of cello, we're approximately at the same point where computer science was in the 50s. And we are nearing a point where we IT people can take over. They don't need to know anything about the underlying systems. We can build on top of that. And that's why I want, like in 5-10 years, I want to program living things. I don't want to program computers anymore. Yeah.
How to get involved with biotech as a software engineer without spending hundreds of bucks on some home lab equipment?
You have some groups, some biohacker groups that pop up where people get together. They share the cost of the equipment and they do experiments. And there's a lot of information online on how to do this.
Any specific courses or tutorials or communities online maybe?
Yeah, you have the Biohacker Lab for once, yeah. If you give me your email address or something like that, I can send you a couple of links.
Cool, great.
Yeah.
Thank you for the talk.
Yeah, thanks.
Any more questions? Then I have a question. So you told us that there are 2 new genes, right?
Yeah, well, we have made a new base pair. Yeah, the X and Y.
So basically, we can, we can use DNA like a storage. So for now, we have a storage with not a base of 4, but with a base of 6.
We can already do that today. Do you know what the most published book ever has been? Well, it's not the Bible or anything like that, which it used to be, I think. But it was a scientist who wrote his book in DNA. And he went to sleep. The next morning, he had 1 million copies. No, 1 billion copies, yeah. So we can already use the DNA as information storage. What these X and Y will do, if they have a purpose of operating in the cell, we don't know yet. Or if we can just use it to store extra information. But it gives us 2 more bits to work with.
Yeah. That's cool.
Yeah.
And one more question. Could you explain how this RNA structures work? So RNA is like a string, yeah?
Yeah.
And each gene is like a connector, which pairs another specific gene from this 6.
A gene is a collection of parts of the DNA sequence. So when we have been analyzing this stuff, we have seen that when we analyze the DNA of many different animals, we have or species, we have seen that these who have this bits in their DNA, they are able to do this. Those who don't have these bits, that part, and that part, they can't do that. So that's how we classify things into alleles and genomes, and yeah.
Are these sequences different in length?
What?
They're
different in length.
And these structures, they made from a single strand of RNA, right? You mean like a few slides before when from single RNA structures? Yeah.
Oh yeah, these ones.
Yeah.
Yeah. These are just using the RNA to bind, because the DNA already has bound, and the A always binds to T, the D always binds to C in that way. So when you're creating a new baby, then in meiosis you split the DNA strand and then you fill out the other parts, so you have two copies of it. And when you are going to, when your operation inside the cell, then you will take parts, you have some things that come to the DNA, you will copy part of it and make it into RNA, single-stranded RNA, which then will create proteins to use within the cell.
Mm-hmm. Any more questions?
Is there any actual jobs for living programming now? I mean, in labs or in any institution, maybe military?
I just moved to India, and I had a friend there who has a friend in England, which runs a biotech company. And he said that, yeah, well, if you don't have to get money for it, well, then you can you could probably join in some companies and start learning some of this. There are not too many companies that are doing this synthesizing or writing code yet. That's experimental. Like 3 months ago, they released the cello from MIT. But I really hope those possibilities will come along, because I would gladly like to join in on it.
Okay, thank you.
Are you amazed, guys? Applause to Kristoffer.
Thank you.